All right, so this is an example of what we're going to call static rotational equilibrium. In other words, this just means that the system is not moving and there are balanced torques. So static means not moving and equilibrium means balanced. If you recall from linear motion, we had equilibrium problems with tension where we had multiple tension forces and they were all balanced, so the object wasn't moving. Well, it's very similar in this case. So let me read the problem statement. We have a 5 kilogram mass placed 25 centimeters to the left of the origin. So this is 5 kilograms, and it's going to be 25 centimeters to the left. We also have a 2 kilogram mass. So this mass 2 here is 2 kilograms, placed 15 centimeters. So R2 is going to be 15 centimeters to the right. And then an unknown mass, I don't know this mass, is going to be placed 23 centimeters. I am given that information to the right of the origin. And so if the system is in static equilibrium, in other words, it's not moving, what is this unknown mass? So what is mass 3 in kilograms? Can I solve for that? All right, so I'm given a lot of information about the masses and their distances, but before I solve the problem, I really need to make a note to myself that because I'm thinking about static equilibrium, the most important given information in this problem, right, is that my angular acceleration is going to be 0. Right? I'm not accelerating. I'm in static equilibrium. I'm not even moving, right? So my angular velocity, is also going to be 0. Initial, final doesn't matter. It's never going to change. So therefore, right, if my acceleration is 0, then what is my net torque? Well, if net torque equals I times alpha, and alpha is 0, then my net torque is also 0. So when you're solving equilibrium problems or problems where there are multiple torques on a system, but the system's not moving, then it's important to note that my net torque is going to be equal to 0. That is probably the most important piece of given information I could have. So I'm going to go ahead and just draw a sketch of this setup, a simpler sketch here, and try and identify what torques are actually acting on my system. All right, so if this is my rod and this is the point of rotation right here, I'll just call this point P. What I can do is I can think about each mass hanging on this rod as producing a torque on the rod, right? So if I think about this, if this mass right here, let's say this is 25, I believe 25 centimeters. This mass is exerting a force on the rod, is it not? If I just consider the rod, and the mass is like an external object, then this mass is exerting a force on the rod. How much force is the mass exerting on the rod? Well, it's got to be equal to the weight force, or the force of gravity on mass 1, right? I know that mass 1 is being pulled down to the earth by gravity, and so it must be exerting that force. It's not moving, so it must be exerting the same amount of force on the rod. And so the force exerted on the rod by mass 1 is just, right, that would be just m1 times g, 9.8. And I know the distance away from the center. And so if this is perpendicular, which we know it is, then the torque produced by mass 1 could just be solved by taking the distance, right? This would be r1 multiplied by m1g, right? So weight can also be a torque. We can also have torques provided by the force of gravity on objects attached to this rod. So I can do the same thing for mass 2 and mass 3. If this is mass 2 right here, then this is going to be the force of gravity on mass 2 that's pulling on the rod. That would be equal to m2 times g. And that would be, so the torque produced by mass 2 would be the lever arm, or the distance from the center, multiplied by mass 2 times g. And same thing here for mass 3. Okay, that'll be equal to m3 times g, or in other words, the torque would be r3 times m3g, right? The lever arm times the force. So this is going to be the force of g on 3, and therefore the torque would just be that same force multiplied by the distance from the center, r3. So this I've been given, right? This is going to be 15, that's r2. This was r1, and then this distance is going to be 23, and that was my R3. All right, so now let's think about the direction of each torque, right? I know that the net torque has to be 0. So in other words, I could also think about it like this, right? If the net torque is 0, then that means all of the clockwise torques are going to equal all of the counterclockwise torques, right? They have to. All of the torques trying to pull the system clockwise must balance all of the torques trying to push it counterclockwise. And so if I know this to be true, I can actually just say then, I can decide which torque 1, torque 2, and torque 3 are counterclockwise and set them equal to the ones that are clockwise. But you'll see here that it actually is pretty intuitive. If I look at the left side of that point of rotation, so mass 1 is trying to make the system rotate in which direction, right? Like this, right? It's going to rotate like this. So what direction is that? That's going to be counterclockwise. So that's going to be my positive direction. How about mass 2 and mass 3? They're going to try and pull the rod in this direction. What direction is that? That's clockwise. So that's going to be negative. So I see here that it actually works out that on either side of the point of rotation, just all of them are positive on the left side, and all of the masses on the right side are producing negative torques. So in other words, the torque produced by the first mass must be equal to the sum of the torques produced by the second and third masses. Now, if you're not convinced, don't take my word for it, right? We could also look at each torque separately and consider the sign. If torque 1 is positive and torques 2 and 3 are both negative, I could also say that torque 1 minus torque 2, right, plus a negative, minus torque 3 is going to be equal to 0. So in other words, torque 1 is equal to torque 2 plus torque 3. I get the same expression no matter how I decide to think about it. So then I'll plug in my values for torque 1, torque 2, and torque 3. And this is very important. You don't need to make the distances negative here. So I know when we did center of mass, we defined the origin to be 0, and anything to the left of that was negative and to the right was positive. But in this case, we're already accounting for the sign of the torque by the direction it would rotate the system in. So we don't need to double count that by making the distances here negative. Leave the lever arms all positive when you're solving torques. So torque 1, that would be R1 times M1 times G. That'll be equal to R2 times M2 times G plus R3 times M3 times G. I notice that there's G in every single term, so I'm going to cancel all my G's, get rid of all those. And that would be equal to R1 M1, so lever arm of 1 times mass of 1, right? R2 M2 plus R3 M3. And so if I rearrange this equation for M3, because that's what I'm looking for, everything else is a known value, I'm going to subtract that R2 M2 term and then divide by R3, the coefficient of M3, and I'll get an equation that looks like this. R1 M1 minus R2 M2 divided by that third lever arm, right, R3, will be equal to the mass 3 in kilograms. So then I can plug in my values and solve for mass 3 directly. So R1 here was 25 centimeters, but in this case, I actually don't need to use meters. If you see, you have R on the top and on the bottom, so your units for length will cancel no matter what you do. I'm going to just go ahead and convert them to meters anyways, because that's best practice though. So that would be 0.25 multiplied by mass 1 was 5 kilograms, minus our second lever arm here was 15, so 0.15. Multiplied by 2, that was our second mass, and that would be divided by the lever arm to mass 3, which was 0.23 or 23 centimeters. So that would be equal to 4.1 kilograms for mass 3. So if mass 3 is 4.1 kilograms, that will balance my system and I will be in static equilibrium. Now I want to point out that you could also solve this problem using the definition of center of mass if you'd like to. If you know that the center of mass needs to be at the origin and you consider all of the masses and the rod as one big object, then you could solve for where that third mass would need to be placed so that the center of mass was in the middle. But when we solved center of mass problems, right, we considered everything as one big object. So the masses and the rod were one big object. That's why we didn't talk about torque before, because there was no torque, right? There was no external force. There was just 3 masses attached to a rod. They were all one object. Now we're not considering the masses as part of the rod. We're looking at the rod by itself. The center of mass of the rod by itself is still right here. And now we have these external masses that are producing torques on the rod. So I just want to point out that there are two different ways of thinking about the same thing. Center of mass and torque are very similar concepts. So again, you could have solved this problem using center of mass as well, but it's a bit simpler to use net torque. And in this case, we knew that the net torque had to be 0, and we were able to use that to solve this problem.